Hello, Prof. Prof. Wang, can you hear me?
Hello. Yes, I can hear you.
Okay. I think our tutorial is scheduled at 10 p.m. Beijing time. So now it's 10 o'clock. So I think we can start now. Are you okay?
Yep, I'm ready.
Okay. I will prepare the video recording. Okay.
Okay, so let me begin.
Uh,
Okay.
okay.
Will you
Okay. Sorry, Prof. Wang. Let me first give an opening remarks for our
Okay,
tutorial.
sure.
Okay. Thank you, everyone. Thank you, attendees. This tutorial is a CVPR tutorial on mobile visual analytics, and I am Chen Tao from Fudan University, Shanghai, China, and I'm very pleased to host this tutorial, and I am also very glad to have you attend this tutorial. We are a group of researchers from China, including me, Professor Huang Gao, and Dr. Yu Gao. Yes, from both academics and industries. Please let me introduce why we organize such a tutorial on mobile visual analytics. As we all know, in these years, the computer vision has achieved greater success with the aid of deep learning techniques. As we know, this success can be greatly attributed to the high computational power and large volume data. But in many scenarios, such as the autonomous vehicle and mobile video and other everyday scenarios with limited access to the computational power, the artificial intelligence deployment on the mobile device is very urgent and also extremely important. In everyday life, we want to deploy the various tasks. For example, the mobile face recognition, mobile augmented reality. These tasks, if you want to explore these tasks on the mobile device, then you need to study how to compress your AI models and how to design your AI models and how to design various vision algorithms according to the mobile specifics. For example, the dynamically changing context and the dynamically changing scenes in the mobile captured videos. So considering this, we organize such a tutorial on mobile vision analytics, and we focus on two aspects to address two key problems in this tutorial. The first one is how to design a compact and efficient backbone for mobile use. And the second one is how to utilize the contextual information captured by a mobile device and utilize such context information to help analyze the visions, the images, the videos, and the various tasks around the mobile device. So this is our focus in this tutorial. And we also want to hear from you, and we are very pleased to accept your suggestions and comments regarding this tutorial. Okay, so now I will give the time to Professor Huang Gao on the first presentation, followed by Dr. Yu Gang from Tencent Company, which is a giant internet company in China, and lastly by me. So Now, Professor Huang, are you ready?
Yes.
Okay. So
Okay.
now I give
Let's
time
go.
to you. Okay.
Okay. Thank you.
Mm.
Okay. Hello, everyone. I guess some of you are in the evening, and some of you maybe, and some of you are maybe in the morning. I think in the United States. Okay. So the topic of this tutorial is convolutional networks for mobile applications. So this part of tutorial basically will cover the backbones for visual applications, as Professor Chen just introduced. So I'm Gao Huang from Department of Automation at the Tsinghua University. So as we all know, deep learning is a popular technique that has been applied to many different areas, such as the medical AI and the basic sciences, etc., and the self-driving cars. So many of them are for computer vision. So in this part of the tutorial, I basically will cover 3 parts. In the first part, I will talk about the backbone design for convolutional neural networks. That is basically the architectures that were designed for general visual applications. And in the second part, I will talk about the handcrafted architecture design for, especially for mobile devices, which has, so basically these backbones are very compact that can run on cell phones or other wearable devices. And in the third part, I will talk about a research direction that our group are actively working on. That is the dynamic convolutional networks, which are especially suitable for mobile applications. Okay. So this slide basically shows some of the representative convolutional networks that were designed in recent years. Of course, it includes the classical NONET, which was designed in the 1990s, and also the many other architectures. I guess all the audience are quite familiar with, like the AlexNet, ResNet, etc. So why architecture matters? Why we need so many architectures, and why people care about the architectures of deep neural networks? So the reasons are that the architecture actually affect the representation power of neural networks. So different architectures may have different representation power, which is very important for deep learning. And the optimization difficulty for different architectures is also varies. In other words, the difficulty to train different architectures can be very different. And also, different architectures may lead to different generalization ability, and of course, the efficiency also depends on the architectures we're using. So in this slide, I'm basically divide the development of convolutional networks in recent years into 3 stages. So this is basically my personal opinion. In the first stage, I think it's called the fast developing stage. So the stage starts from the AlexNet. So in this stage, people are aiming at designing deeper and larger networks that have higher efficiency. So basically, the main objective is pushing for better performance in terms of accuracy. So the most important work is the AlexNet, and there are also many other influential work such as VGG, GoogleNet, etc. So this stage starts from 2012, and it basically lasts to 2015. And in the second stage, I call it the mature stage for convolutional architecture design. So in this stage, people are also pushing for higher accuracy, but people are also like to identify what are the key factors that have the greatest influence on the performance of convolutional networks. People want to find the simple principles that are most critical for a deep network to have good performance. So in this stage, the ResNet and the DenseNet architecture are perhaps the most important ones, because actually for ResNet, although it can go very deep, but the design principle is actually very simple. You just need to add the identity connections to a deep network. And the DenseNet is also very simple. The design principle, you just connect every layers, every layers in the network. So in this stage, people find, well, we don't need very fancy architectures. We just need to follow very simple principles. Then we can end up with very powerful architectures. So in this stage, the architecture design, the research on architecture design for CNN is kind of going mature. And from 2017 and to present, I call it's prosperous stage, because at this stage, people find the deep network can be applied to many real applications. And in this stage, people are pushing for a better trade-off between the accuracy and the speed. Okay, and so that's a lot of work focused on designing net-weighted models like the mobile net, the condensed net, the shuffle net, which will be covered in this tutorial. And also many of the researchers are interested in designing architectures by algorithms. That is, we want to automate the process to designing convolutional architectures. So this is a popular research direction called Linear Architecture Search, NAS. Due to time limit, I will not cover this topic, but I think as this is a very hot topic, you can get the information from other workshop or tutorials. And also another research direction is called dynamic neural networks, which will be covered in this tutorial. So basically, all the aforementioned models are basically static models. In other words, once those models are trained, then the architecture is fixed, and all the parameters are also fixed. But for dynamic networks, the architecture or the parameters can change, depends on each individual input. So this is called dynamic network. And this tutorial will talk a lot of interesting work on this direction. And of course, transformers in computer vision maybe starts from early this year. Transformers are getting very popular in the area of computer vision. And I think you can also find workshops on this direction, but this tutorial I will not cover this topic. Okay, so this is my personal opinion on the development of seeing architectural design in the past about 10 years. Okay, so as we will talk about the deep learning for mobile applications. So our goal is to designing deep models that has no compute, low latency, and a low memory cost, such that they can be applied to cell phones, wearable devices, robots, drones, etc. So let's now get into the details of the design of mobile CNNs. So as most of the mobile convolutional networks are depending on a specific type of convolution, I will start with the group convolution, which is very important for designing net-weighted convolutional networks. So the basic idea of group convolution is very simple. just has the right image in this slide shows, we basically split the channels into different groups. And there are only connections within each group, and there's no connections across groups. So compared to standard convolution, which is shown on the image on the left, the group convolution is sparse, right? So it has much less connections because there are no connections from the red channels to the green channels. Okay, so in this way, the computation will be cut by a factor of G. So G is the number of groups. So just as the image shown here, if we have 3 groups, okay, then the connections is only 1/3 of the standard convolution. So this is a significant saving in number of parameters and the number of computation. So of course, the group convolution, because it's sparse, it will sacrifice some accuracy. However, as there are a lot of redundancy in convolution, so this kind of sparsity ultimately is more efficient. Although it will sacrifice some accuracy, but the efficiency, the gain in efficiency is more significant. So basically, the gain in efficiency ultimately outweigh the performance drop. So the group convolution will turns out to be more efficient than the standard convolution. So this kind of convolution is adopted in AlexNet. So that's our O'Neill work, and also adopted in ResNext. And the condensed and ShuffleNet, which are 2 mobile CNNs, which will be discussed in later slides. Okay, so this is a group convolution, and if we go to the extreme, that is, if each group has only 1 channel. So basically, in these slides, each group have multiple channels. But if every group has only 1 channel, then we will end up at a so-called depth-wise separable convolution. So this kind of convolution is very efficient because, you know, if you have C channels, then the computation will be cut by a factor of C. So as the C is usually very large, so the saving in computation is very drastic. So this kind of depth-wise separable convolution is adopted in many SOTA mobile CNNs like MobileNet and ShuffleNet, and also adopted in this architecture obtained by last models, neural architecture search. Okay, so these are the group convolution and the depth-wise separable convolution are the building blocks, are the basic building blocks for mobile CNNs. So let's get into the most representative mobile deep networks. So the most popular one is perhaps the MobileNet series. The first MobileNet was developed in 2018. I guess it's put on archive in 2017. So the key idea is the depth-wise separable convolution I just introduced. So with this depth-wise separable convolution, the network can be very efficient. And the authors show that it can run on a iPhone in real time for object detection. So which was quite impressive. And also the network can get pretty good performance on ImageNet and on Coco detection. And 1 year later, the second version of MobileNet was developed. So the key idea in MobileNet v2 is to introduce the so-called inverted residues and the linear bottlenecks. So in a ResNet, we have the bottleneck structure. That is the convolutional layers to learn the residue usually has fewer channels than the in the main path of the network. So which is called the bottleneck structure. So you compress the number of channels and do the 3x3 convolution, and you use the 1x1 convolution to expand the number of channels again and add to the output of the identity collection. So the authors find this kind of design will lead to more overhead on mobile devices, because you need the memory copy, so the identity collection. In that path, you will need to store more channels. So the inverted residue block is basically you expand the number of channels within the residue unit, and the identity mapping only needed to copy a compressed number of channels. So this is going to give you more speed up in real devices. So this is the key idea in MobileNet v2. And in MobileNet v3, they basically introduced the neural architecture search. They basically combine the hand crafted design of deep networks and combine it with the neural architecture search. So as the plot on the bottom right shows, the blue dot shows the accuracy and speed trade-off of MobileNet v3, and the blue dots are MobileNet v2. So we will see this significant improvement in terms of efficiency when the neural architecture search is being applied here. So actually, up to now, the MobileNet v3 is still one of the SOTA models in terms of accuracy and speed trade-off. Okay, so this are basically the MobileNet series, and another line of another series of popular mobile CNNs is the ShuffleNet. The ShuffleNet v1 is also a CVPR18 paper that was first put on arXiv in 2017. So the ShuffleNet is basically designed on top of the ResNet architecture. So the idea is also to split, to use the group convolution and the depth-wise separable convolution. So the key idea is the motivation is they want to replace the 3x3 convolution in a residue block by depth-wise separable convolution. So that's the motivation. Because the 3x3 convolution constitutes the majority of the computation in each residue unit. And when the 3x3 convolution is replaced by depth-wise separable convolution, then the majority of computation goes to the 1x1 convolution. And then they also find, well, when the 1x1 convolution becomes more expensive, so they replaced they're then going to replace the 1x1 convolution by group convolution. So then they end up with the replace the 3x3 convolution by depth-wise convolution, and replace the 1x1 convolution by group convolution. And then they find when they design the module in this way, the channels will have 3 independent paths, and they cannot talk to each other. So there's no, you basically have, if you have a number of G groups in the 1-by-1 convolution, then you will have G independent path, and these paths are independent and do not talk to each other, and they find this will sacrifice accuracy. So they introduce a channel shuffle. They call it the channel shuffle layer. Is basically when they have the first 1-by-1 convolution shown here, the introduce a channel shuffle layer that they mix different channels in different groups, so that the information can mix through this layer, and then the output is sent to the 3-by-3 depth-wise convolution, and then the 1-by-1 convolution, and this can greatly boost the performance. So that's why they call it the shuffle net. In other words, when they use a consecutive group convolution, depth-wise convolution, and group convolution, they lead to introduce a shuffle layer to mix the information in different groups. So that's the key idea of ShuffleNet V1. And then probably half a year later, in ECCV 18, they designed the ShuffleNet V2. In this paper, they kind of introduced the feature reuse with dense connections. There's a similar idea from DenseNet, but they have a mild feature reuse. In DenseNet, every layer have connections to the features of all previous layers, but in ShuffleNet V2, they only reuse a subset of features from previous layers. And also they have special design for hardware efficiency. And for more details, you can refer to the original paper. So these are the two ShuffleNet work. And then as the ShuffleNets are built on top of ResNet, and the CondensNets are built on top of DenseNet. So the three figures shown here basically shows the original architecture of DenseNet, and the architecture of CondensNet V1, and the architecture of the CondensNet V2. So the idea is actually also simple. So in DenseNet, as shown on the first figure, you basically in every layer you reuse all the features from previous layers. Okay, so this is DenseNet. So you can imagine if you have many layers, for example, you have a 100-layer model, then the 100th layer will use all the features from the previous 99 layers, so which are superfluous and may have many redundant information. So then the CondensNet proposed to remove some of the redundant connections. Well, you may some of the features may be unnecessary, so we can prove some of the dense connections. We do not need a full dense connected model. So that's the key idea of the CondensNet V1. So they basically specify the dense connections. And they also propose so-called learned group convolution to make the connection removing have less effect on the accuracy. Okay, so that's the first version of CondensNet. And in the second version of CondensNet, they find instead of simply removing some of the features from previous layers, they can revive these features by updating them. For example, the first layer may be redundant for the layers in the maybe in the 20th layer or later. And if you simply remove that connection, it will still result in some accuracy drop. However, if you use a little bit computation, you can update this feature and you can make it useful again. So that's called feature reactivation. And this is going to be more effective than you simply remove some of the connections in CondensNet V1. So these are the two versions of CondensNet. Okay, so basically the mobile nets, shuffle nets, and the condensed nets are all, the first version all appears in 2017, almost in the same year, and they all published on CVPR 18. So, probably in 2017, people find, well, the SOTA models can, the vision models can be put on mobile devices, and there are many other work that are built on top of the work I just introduced. And due to time limit, I will just introduce these 3 types of mobile CNNs in the second part of this tutorial. Okay. So up to now, the architecture I just introduced are static models. And in the third part of this tutorial, I'd like to talk about the dynamic convolutional networks, which my group are actually actively work on in the past 2 years. Okay, so why do we need dynamic neural networks? Why dynamic? Okay. So if we take a look at these plots, so basically it shows some of the deep networks, the accuracy and the computational cost trade-off of some typical convolutional networks like AlexNet, CuckooNet, ResNet, DenseNet, etc. So we can see a clear trend, you know, from this plot, we can see a clear trend that on ImageNet, on the large scale data set, larger models is better than smaller models, right? So when we go right, then the computational cost is higher and the accuracy is also higher. So why we need the larger models, right? Because small models is more user-friendly on mobile devices, but for this very cumbersome models, you cannot put it on your cell phone. So our question is, why larger models are better than smaller models, right? Why do we need these larger models? Why they outperform this the smaller models? So there are many reasons, and I can give you a very interesting example why bigger models is better. So here I show a picture of an object, and I'm not sure whether or not you can recognize this image. What object is in this image? So actually, this is a picture of a horse, but it's taken from a weird angle, right? So we cannot see his eyes because his nose is just in front of the camera. Now we can only see his nose and his ears. So for this image, it's not very easy for we humans to recognize, and it also is difficult for a deep model to correctly recognize what's in this image. So in order to correctly recognize this is a picture of a horse, we probably did a 50-layer model or maybe a 100-layer model, because it's quite challenging task. However, in our data set, many of the pictures are actually very simple, just like the image shown here. Like this picture of a horse is actually very the features are very clear, and we can, like we humans, we can immediately recognize, well, this is a horse. And I'm pretty sure that for a deep network, this is going to be easy as well. I think a 7-layer AlexNet can correctly recognize this as a horse. So for we humans, we apparently we spend less computation on the left image and we spend more computation on the right image. So that's our human visual system can has the ability to dynamically allocate our computation to different input. However, for deep networks, the computation is fixed. For example, if we have a 50-layer ResNet, then no matter for the left image or the right image, we all need to inference from the first layer all the way down to the 50th layer. And the computation is the same. So in order to correctly recognize the right image, we need to make a model very big. However, this bigger models is very redundant for the left image. So this is the dilemma. So then our question is, why do we use the same expensive model for all the images? So can we like use a small network to recognize those easy ones, easy inputs, and use a bigger model to recognize a large image? So then this is basically the motivation for dynamic networks. So we want to have an architecture that it can change condition on the input. For easy ones, it can have a reduced architecture, and for hard image, it may have a full-sized model to correctly recognize a hard input. Okay, so for dynamic networks, I will talk about 3 types of dynamic models. So here is a hierarchy of dynamic neural networks. There are actually many different types, and in general, we can split into the so-called sample-wise dynamic networks. That is, the architecture or the parameter will change condition on different samples, just like the 2 horses are just shown in the slide. So the architecture may change its architecture for each input, and also there are dynamic networks that can perform spatial-wise adaptive computation. That is, given one image, you can dynamically allocate computation to different pixels or different regions in the image. And there are also temporal-wise dynamic networks. That is, the network can allocate computation dynamically along the time axis. That is, this is particularly useful for video recognition or time series data analysis. Okay. So this is a hierarchy of dynamic networks, and the dynamic networks can have a dynamic architecture or dynamic parameters. And for dynamic architecture, it can have a adaptive depth or adaptive width or dynamic routing, etc. So let's first give a brief review of the dynamic depth network. So the first type of dynamic depth network is using the early exiting technique. The key idea is we first build a deep network, and then we add intermediate classifiers to the architecture. And for some hard ones, it may influence the full model. But for some easy images, like the picture of the horse shown here, it may exit from an early stage of the network. So in this way, some of the easy ones will not go through the full model to get the results. So it's going to be more efficient. Okay, and the early exiting can be implemented in 2 ways. The first idea is you simply cascading different models. For example, you have a 18-layer ResNet, and you have a 34-layer ResNet, and you have a 50-layer ResNet, and then you cascading these 3 models, and all the images will be sent to the first model, and you have a router that decide whether an image will be sent to a deeper model. And there another way is just like I introduced, you have a deep model and you have many intermediate classifiers, and at each classifier you will make a prediction, and you also decide whether you need to keep inference the subsequent layers, or you will stop there. So these are two different implementations. Okay, and a challenge in designing early exiting models is that in convolutional networks we have the feature hierarchy. That is, we have the so-called the downsampling layers in middle of these models, and the feature maps keeps the resolution of the feature map will keep shrinking in the network. And in such a architecture, we usually find that the earlier features are not ready for classification, and only those cost level features in the end of the network will have a decent classification accuracy. So this causes a dilemma. That is, the classifiers only work on these cost level features, and if we attach all the intermediate classifiers to those cost level features, then we can actually save low computation, because when we get to the first classifier, the computation has already been used. Okay, and if we attach the classifiers on top of the earlier features, the fine level features, then the accuracies are unacceptable. So so this is our work in 2018. So we designed a new architecture called the multi-scale architecture. So basically, we reorganize these features and design a 2D architecture. And in this architecture, the horizontal axis corresponds to the depth, and the vertical axis corresponds to the scale. And all the connections going from up to bottom, or they are downsampling layers. And in this architecture, we will see that all the classifiers, all the intermediate classifiers are attached to these cost level features, and all the classifiers can get decent accuracy. So that's why we need such a multi-scale architecture. And so in this architecture, so the training of this model is we just use a very simple technique that we just add all the loss of these classifiers to sum them up and perform a gradient descent on these classifiers, just like a training canonical convolutional networks. And during the inference stage, we will first inference the first classifier, and we will check the confidence. If it's smaller than a given threshold, that means the classifier is not very confident. It will be sent to a second classifier, and until it hits a classifier that the confidence is larger than a predefined threshold, and then the inference procedure will stop, and all the rest features will not be computed. So we will see that for each input, it will activate a specific number of classifiers. For example, for some easy ones, it will only activate the first classifier. And if we have a harder one image, it may activate all four classifiers shown here. So in this way, actually the network depth is changing depend on the input. So that's why we call it a dynamic network. Actually, it's a dynamic depth network, because the depth is changing dynamically conditioned on the input. Okay, so using this architecture, we can get pretty significant improvement in terms of efficiency. So basically the left plot shown here is the results on ImageNet, and the x-axis shows the computational cost, and the y-axis shows the accuracy. And the three black curves shown here are corresponds to the or multi-scale dense net, that is or MSDNet for short. So these are the three black curves shown here corresponds to the or dynamic MSDNet. And we will see that it outperforms the DenseNet and the ResNet by a large factor. So basically, it achieves 2 to 5 times speed of over DenseNet. And another advantage of dynamic networks is that it can adjust the computation cost on the fly. If we go back to this slide, so we have the threshold shown here, and the threshold is just a scalar. If we increase the threshold, then the network will be more conservative. It will use more computation and to achieve high accuracy. And if we lower down the threshold, the network will be more aggressive and in terms of early exiting. So basically the computation will be reduced, but the accuracy will have a drop. And basically we simply tune this threshold, we can get a trade-off curve shown here. So that's why the black curve is the solid line, solid curve. And for these red dots, these are DenseNet. So they are low models between two dots. So they are connected by dashed line. So in other words, the dynamic network can adjust its computation online by simply tuning a threshold. You don't need to retrain a model. So this is an advantage over the static model, because for a static model, when you train a 50-layer model, then the computation is fixed. So you cannot change the cost on the fly. And so that's why the dynamic network is especially suitable for mobile applications. Because if your, for example, your cell phone is in no battery, and you can tune the threshold down to save energy, and you also need to sacrifice some accuracy. But if you want to push for performance, then you can tune up the threshold. You can then you can get better accuracy, but you will the model will be more energy consumption. So finally, for this model, we have a visualization. We want to see what are the easy images identified by this model, and what are the hard ones identified by the model. So these are two classes. The red one and the volcano are two classes from ImageNet, and the pictures shown on the left are those exiting from the first classifier. So these are the easy images identified by the model, and the images on the right are the hard ones. And I think for we humans, we will find the images shown on the left are relatively easy. For this, for example, these volcanoes are very, the features are very clear. And for the images on the right, they are more complicated. And this is a toy volcano. Okay. Okay, so this I just introduced the dynamic depth network with early exiting. And another way to achieve dynamic depth is so-called layer skipping. The layer skipping. The idea is that consider in a ResNet-like architecture, you have a regular ResNet block, and you have a gating module, which controls the activation of the residue path. For example, if the output of the gating module is 1, then you activate the residue path. You activate the convolution, and this is a nominal residue unit. However, if the gating module output 0, then the convolution path is blocked, and we only have the identity connection in this unit. And we will see that in this way, the depth is reduced when the gating module output 0. So this is one simple idea to achieve the dynamic depth using the a gating module to control whether a resident unit will be skipped or not. And another idea is we design a global policy network. So in the gating module, the gate only controls the resident unit, the activation of a residue path within one block, one resident unit. And we can also have a global policy network that determines the activation of these blocks globally. And this policy network is usually trained via reinforcement learning. So these are two types of dynamic depth network. And similarly, we can have a dynamic width network. And the idea is for some hard ones, you may need to activate a wider network or a fatter network. And for some easy ones, you only need to activate a very thin network. And the idea is the most straightforward idea is to skipping the channels, right? You have a gating module to control whether a channel will be skipped or not. Usually, the most straightforward is designing a gating module that decides whether or not a channel will be skipped or not. So there are multiple work references that use this idea, which are listed below in this slide. And another idea is we first inference an image through a thinner network, and then we get the final prediction. And if the prediction has low confidence, then we inference a wider subnetwork and a even wider network. And when the full model is inferenced or the confidence hit or predefined threshold, then the inference stage will be stopped. And another idea to achieve dynamic width is so-called mixture of experts, or MOE. And there's a soft MOE. Basically, you have n experts, and you have the coefficients from alpha 1 to alpha n, and these alphas are known through a weighting module. So these alphas are data dependent, or in other words, they are dynamic. So they basically decides how we weight these experts, the output of these experts. And the hard MOE is known a gating module that decides whether an expert is activated or is not activated. And so these networks basically activate the network modules in classical architectures. And there's another dynamic architectural network called dynamic routing. And they basically use the tree structure or multi-scale structure. And for each input, it will activate a subnetwork in this supernet. And due to time limit, I'm not going to go into the details. And in parallel to the dynamic architecture, we can have we also have the networks with dynamic parameters. In other words, the network parameters is conditioned on the input. Okay, and there are three types of dynamic parameter networks. One is one is using the parameter adjustment, and the one is is parameter prediction, and the other is dynamic features. And let's go to the details of this different dynamic parameter network. So this is the regular convolution. The yellow squares shows the input features, and the squares on the bottom shows the filters or the convolutional kernels, and the filters is applied to the features to compute to convolve on the input features to get the output feature. So this is a classical convolution. So this is the regular convolution, and if we want to make it dynamic, then we will introduce, the first idea is to introduce a parameter adjustment module. And this parameter adjustment module will modify the original parameters. And then the modified filters, or we call it dynamic parameter, then they're applied to the input feature to compute the output feature. So there are different ways to achieve this kind of weight adjustment. The first one is called weight ensemble. So we learn a set of weighting factors, the alphas, and the alphas is applied to we have a multiple set of filters, and these alphas are applied to reweight to compute a weight sum of this different set of filters, and to obtain a dynamic parameter, and then it's applied to the input feature to compute the output feature. So this is called the weight ensemble or dynamic ensemble of filters. And a more direct way is to use the weight prediction. That is, the parameters is directly being predicted from the input feature, and then the dynamic parameters is applied to the input feature. So this is called direct weight prediction. This is a more direct way to generate dynamic parameter network. And there's also a very interesting type of dynamic parameter network, which is called deformable convolution. That is, the kernel shape is dynamic condition on the input. So we call it kernel shape adaptation. And the most representative work is the deformable network. And the weight adjustment, the weight adjustment technique I just introduced is to learn a different set of weights, the alphas, to reweight the different kernels to get the final filter weight. And this is in somehow equivalent to reweight the input features. To see this, we can write a simple equation to show its equivalence. So in other ways, a dynamic reweight of the filters is equivalent to a dynamic reweight of the features, right? And based on this motivation, we can simply use the attention module to reweight the input features. So I think most of the audience are familiar with attention, and the attention can be applied to different channels, and this can achieve a similar effect of reweighting kernels. And a most representative work is the squeeze and excitation network, which was proposed in 2018. Okay, so this is the dynamic parameter network. And finally, I will spend a little bit of time on the spatial-wise dynamic network and the temporal-wise dynamic network. I will go through this part very quickly. So why spatial adaptive? If we take a look at the image and uncover this image, and what we can recall, what objects have we identified from that image? We probably identify this car in the middle of the image, and there's a building behind this car. This is a street view image, right? But for more details, we probably have missed. If we take it again, take a look at it again, and we'll see there's a motorcycle on the left, there's a McDonald's on the right, etc. So basically shows for we humans or visual system will put more focus on specific areas of the input, and we may spend less computation on the background pixels, right? So this is also called the saliency identification or saliency prediction. And so our human visual system is very efficient because we only put our attention on a specific set of pixels in the image. But for convolutional networks, the convolution is scanned from the top left to the bottom right, and every pixels have an equivalent amount of computation. So obviously, this is pretty redundant, right? For self-driving cars, we only care about the traffic condition on the roads, and we do not care about what's the color of the curtain of the building on the side, right? So can we develop deep networks that also can adaptively allocate computation spatially, right? So that's our motivation. And in last year, we developed a spatialized dynamic network called sampling and interpolation. The idea is actually is also straightforward. So it has 3 modules. The first module is called a sampling module, and the sampling module is to learn a sparse mask that decides which pixels we need to spend more computation, and then it will facilitate a sparse convolution to only compute the features on these specific locations, and then we'll obtain a sparse feature map, and then the feature map is interpolated to a dense feature map using interpolation, and the interpolation is very efficient, and this sparse convolution is more efficient than a standard convolution. So this kind of design will save a significant computation compared to standard convolutional networks. And instead of and of course, training this network is not trivial because the mask is non-differentiable. So we use the Gumbel softmax trick to train this model. Okay, so instead of dynamically deciding whether each pixel should be computed, we also propose the region level dynamic network. So we can dynamically choose a patch to compute or skip this computation. And in last year, we motivated by the human visual system that process the information progressively, we designed a so-called glance and focus network. So basically, we have a very efficient branch called a glance module. That is, we process a downsampled image with very efficient computation, and then to extract the global information, and then we identify some most informative regions to extract finer local features, and we call it focus. So the step extract the global information, and the focus, it can have multiple steps of focus to focus on different local patches. Okay, so this is the architecture. I'm not going too much into the details. And one interesting technical part is how to identify the informative regions. And we designed a so-called patch proposal network. And please note that this is different from object detection, which we have have the ground truth bounding boxes. But in image classification, we do not have any local bounding boxes. So we have to learn it in a in an unsupervised way. And actually, we use the reinforcement learning to learn the local patches. So due to time limit, I'm not go to too much details. So basically, the basic idea is we use a reinforcement learning algorithm to locate the informative regions in the input. So the reward signal is when we locate a local patch, it should give us the largest reduction in our loss function. So that's our reward signal, and the action is the location of the patch. Okay, so this kind of we call it Glanzner focus network, or GFNet. It gives a significant boost in terms of efficiency. So based on the MobileNet v3, we get a significant boost in terms of efficiency, and we also improve upon the RegNet and also EfficientNet. We can, because it's a general framework. If we take a look at this architecture, we will see that actually we can plug in any lightweighted backbone here, and to achieve this kind of efficient iterative recognition process. Okay. Okay, so this is the the results, the real latency we tested on our iPhone XS Plus, and these are few examples. I'm going to skip this. Okay, so finally, I will spend maybe 1 minute in on the temporal-wise dynamic network. So this is particularly useful for video recognition. So as we introduced the redundancy in the spatial dimension, and of course the redundancy in the temporal dimension, because there are many frames that do not contain useful information in terms of video recognition. So we proposed called adaptive focus for network for efficient video recognition. So our algorithm can automatically identify which frames are important, and within each frame, which locations are important. So basically, we combine the temporal-wise dynamic and the spatial-wise dynamic together for efficient video recognition. And this is the architecture, and we obtained pretty significant improvement on multiple data sets, like the ActivityNet. And so to summarize, there are many advantages of dynamic neural networks. So through this tutorial, and have talked a lot about the efficiency, and of course, and actually for dynamic networks, it have better transfer representation power, and also it has adaptiveness because it changes. It can adaptively changes computational complexity on the fly, which is an advantage compared over the static models, and it's compatible to many different tasks, and it's also very general technique, and probably it has more potential for designing more interpretable network, because for the spatial-wise attention networks, it actually also tells us which region it focuses more. So it gives some kind of interpretability. And of course, there's many challenges, right? So for dynamic networks, we still like the theories for how to optimally train these dynamic networks. And the architecture design maybe is not mature as in static models. So mostly the architecture are designed for static models, which are not optimal for dynamic models. And so many of the dynamic networks can only be applied to classification tasks, and it's not trivial to be applied to detection or segmentation. So we still need more work. And there's also for some dynamic models, they are not friendly on hardware devices. So this is for some of the dynamic networks. Actually, there are also many dynamic models that can be efficient on GPUs and other parallel devices, and can be parallelizable. But for some dynamic networks, especially for the spatially adaptive networks, they are not quite efficient on hardware. And also the robustness and interoperability are also needs more work. So they're probably not just a downside, but it may invite more research on dynamic networks and to push for new research directions. Okay, so that's all. And if you're interested in dynamic networks, we have write a survey paper on this topic, and the paper has been put on arXiv. And if you're interested, and most of the materials and have talked in this tutorial, you can find it in the survey paper. And so that's all. Thank you very much.
Okay, thank you, Prof. Huang. Okay, thank you for your excellent talk on the dynamic convolutional network. I think it's a very amazing. When I see its performance outperforms other mobile networks. So now we have several minutes Q&A session. Anyone in this room session can pose a question to Prof. Huang. Okay, anyone has a question?
Okay, if there's no question, then I will stop here and give time.
Sorry, Huang. I think I have a question for your talk. I see your dynamic convolution is very efficient and effective for different inputs, and also you propose the sampling spatial and temporal-wise dynamic convolution. But I think for most devices, for example, for the mobile phones, for the ASIC and FPGA, the hardware is fixed. I mean the accumulator or the adder or the other units is fixed there, and this time when your input is changed, then different activities, different units will be activated or will be routed depending on your inputs. So how can you make sure your dynamic convolution is generalized to all kinds of inputs, and its computational resource can be utilized in highest efficiency?
Okay, so that's a very good question. Yeah, just as I mentioned, there's some dynamic networks that are not very efficient on hardware. However, like for general devices like ARM, like some low compute the mobile GPUs. So there's some dynamic networks like the early exiting network. So every layer, the computation is quite regular. So basically, for each input, the computation can be done quite efficiently. And for FPGA, I'm not quite sure. Maybe that's not very friendly. I'm not quite sure. Yeah, but for many devices that use the general chip like the ARM, etc., this can still be efficient. Yeah.
Okay, so most networks you device are they already being used or being tested on mobile devices?
Yes, many of them. Yes,
Okay.
like on
Okay.
iPhones, etc.
Okay.
Yeah.
Okay. Great. Okay.
Mhm.
Any other one has problem? If no, I think we will go to next presentation. Okay. 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 Thank you, Prof. Wang. Next, I think I will introduce Dr. Yu Gang from Tencent company in China to give his presentation. Before his presentation, I will first introduce Dr. Yu Gang. He is currently a research director at Tencent, and he received a PhD degree from the Nanyang Technological University, Singapore. And before joining Tencent, he was a team leader in MakeV, leading the development of detection of augmentation techniques for mobile and embedded devices. He has published more than 30 papers on top journals and conferences. He is also the winner for more than 10 challenges, including COCO detection and skeleton, wide fish detection, activity measure EVE detection, and wide yeast experimentation. He also received the Microsoft Research East Fellowship in 2011. Okay, Professor Dr. Yu Gang's talk is GAN application in mobile devices. So now I will give the time to Dr. Yu Gang. Are you ready?
Hello, can you hear me?
Yeah.
Okay.
Okay. So now I give time to you.
Okay. Thanks for the invitation. Hi. My name is Gang Yu. From Tencent. The title of my presentation is GAN application in mobile devices. The presentation will focus on the application of GAN techniques on mobile devices. This is the outline of my presentation. I will first give some of the basics in the GAN. Then I will have touched the 4 applications for the GAN. For example, like the face human font tool. And finally, I will conclude this tutorial with a few research directions. This is some kind of a survey for the GAN. The GAN actually is first proposed in 2014 by Ian Goodfellow. And if we look at the right part of this figure, at that time, the generated results are kind of gray faces, and the results actually is very poor. And with the development of convolution network, for example, like with the introduction of DC GAN and PG GAN, we can see the generated results actually looks better. And another trend is that if we look at this right part, we can see that we can also generate like the animals, the landscape, and the food rather than the face. So actually, we can see that the GAN society actually have developed a lot with the recent years. If you are interested in this kind of survey, you can take a look at this kind of paper here in the bottom. The idea of GAN actually is very simple. There are 2 components in the training progress. We use the face as an example. For example, there will be 2 components, the generator and the discriminator. For example, given an input noise, random noise, then we use the generator to generate a face. The target of the discriminator actually is to discriminate whether this input image face is a real face or a fake face. Actually, we use the min-max loss function like this to train this kind of model. Here we have 3 very widely used GAN algorithms. And this kind of 3 algorithms will be used throughout this kind of tutorial. The first one is the pixel to pixel. the input of the pixel is actually kind of an image, and the output is another image from another domain. I will give an example like this kind of sketch. For example, the input is a sketch of a bag like this, and the output is kind of a real bag based on the sketch. Also, we can use the pixel to train this kind of action, like the input is a gray image and the output is a RGB image with the pixel-wise correspondence. If you are interested, or if you are familiar with the semantic segmentation, you will notice some images from the cityscapes data set. And the target of the semantic segmentation actually is the input of this kind of street image, and output is the kind of label map or GT map. For example, the different color refers to different region, like the blue color refers to the car, the green color refers to the trees, and the pink color refers to the driving area. And actually for the GAN, if we use the pixel, we can reverse this process. For example, the input, actually we can use a label map, and we can use the label map to generate a real string image like this. So this is kind of pixel what we will do. And the training of pixel relies on a lot of paired data. However, the paired data actually is very difficult to collect. So then we have the cycle-GAN algorithm. The advantage of a cycle-GAN, actually, we do not need to use a lot of labeled paired data, and we can use the data from two different domains. For example, we have domain data like a lot of sketch images, and we also have a lot of data from another domain like the RGB images. We do not need to have the paired data, but we can train this kind of model based on a cycle loss. For example, we have two generators. The first generator, for example, like G, we use the sketch as an example. We use the first generator, for example, like input is the sketch of bag. For example, we denote it as X, and we can generate a real bag like Y hat. And we have another generator F. The input is a real bag, and the output actually is a sketch of a bag like this one. So actually, if we look at the whole pipeline, we input a sketch, then finally, after two generators, we can have another sketch. It should have some kind of correspondence. So we can use the cycle, the loss, the pixel-wise loss, the perceptual loss to train this kind of model. Also, we can reverse the process. For example, the input is the real bag, and we use the generator F to generate the sketch. And after the sketch, we can use another generator to generate this kind of real bag. So this training is continued based on two domain of data. Then we can finally get a very good like pixel-wise model. And recently there is another very good algorithm called StyleGAN, which can generate very high quality images. For example, the difference between the traditional algorithm with the StyleGAN is that the StyleGAN actually imported the latent code to a latent space W based on 8 FC fully connected operations, and they use the add-in operations to inject this kind of style to the generation process. So the main idea lies on the W space here. So if you are interested in this kind of work, you can take a look at this kind of paper here. Now let's move to the face part. So here we have a very small game. So here I list 8 photos. Can we see which photos are generated and which one are the real faces? Maybe I will give you 10 seconds to take a look. Okay, I will show you the answer. Actually, the answer is that all of these images are generated by the GAN algorithms. So we can see that the image quality of the generated images are very good right now. Actually, if we take a look at the background part, we can see the results kind of weird. For example, if you take a look at this kind of background, the generation is not very good. But if we only look at the foreground, you can see the generated result actually is very pretty good. So this is the overview of the GAN4 phase. Although we, as I just showed you, we can use the GAN algorithm to generate very high quality phases, and also we can do some kind of applications. Here I will address 3 kind of applications, and after that I will give some foundations for if you want to use this kind of GAN applications for the mobile devices. Actually, there's a very large gap between the academic and the industry. For example, in the industry, we need to do the model compression, and we need to use a lot of data to train the model to keep the robustness of this algorithm. So I will put these kind of techniques here in the foundations. So let's move first to the applications. The first application is to generate a cartoon face. For example, given an input of your image, we can generate a cartoon nice photo for your image. For example, here I list several styles for the cartoon images. The first row, actually, they have very small ID changes. For example, they look very similar to your identity, but they have very weak cartoon style. But on the third row, actually, we can see the ID changes a lot. It is very difficult to see whether it's your photos or other photos, because they have a very strong style. They have changed the shape of your face and make your eyes very bigger. So actually, all of these are different, different styles. So for the cartoon generation, there is a very important point is that we need to keep the style, we need to combine the style, the cartoon style and the face ID from your input image. So here are a lot of challenges. Here I list 3 challenges. The first one is that we need a lot of training data to train this model. Actually, the training data is very expensive to obtain. And another challenge is that the robustness of the generation. For example, in the industry, if we only have 8% good generation, it's not enough to put this kind of algorithm into the production. But we need to maybe have 100% of a good generation result. So the robustness of the generation is very good for the industry applications. Another challenge is the fast speed for the mobile devices. This is the training stage or the training pipeline for our algorithm. The first stage, actually, we need to have a labeled training data. For example, we have an image like this, input image like this, for example, a user face, and we have a paired data like this. So we have, for example, maybe 100 image pairs to train this kind of first stage model. The model, actually, you can consider as a very large pixel to pixel model. But we may introduce several other losses. For example, we may change the perception loss to some beta losses. And after the first training stage, then we have a pixel to pixel model, and we use this model to inference a large set of faces, real faces A. So, for example, we may have 1 million face images. We can use the trained model to inference the cartoon results for this set A. Then, although the cartoon result may not be very good, but actually it looks better than nothing, right? So we then use this kind of inference, the 1 million inference face data to train the 6-stage model. It is usually a very small model, for example, which can be run on the mobile devices. And also we have a label set C. The label set C actually is used for training used for adversary training. Then we, for example, because we use the small set, the label set, 100 label set, because they have very good high quality. So we use the adversary training here to make the final results more close to this kind of result. So this is the 2-stage trainings for our algorithm. And here are the losses. If you are interested, you can take a look. And actually, for our import, actually is a whole image, for example, rather than a face, only a face. So assume we have an import image like this. We first do the face detection and the face alignment. We crop the face region, for example, like this one. We use the in pixel-to-pixel network to generate the cartoon result like this. And for the whole image, actually, we do the background filtering. This kind of background filtering is really developed by some kind of traditional methods. And we use the, after we do the background filtering, we can fuse or blend the face region to the background regions. And we change the global ELUT to map to the color tone. Finally, we can get the final result like this one. If we have a video, for example, a video with 100 frames, we can do it frame by frame, and finally we can have the video results. Here are a few results use the Proporz algorithm to generate. All these videos actually are run on the mobile devices. The first few frames actually is the real import user face, and the later frames actually they will change to the cartoon faces. Actually, you can see they have some similarity with the original face, and they also have some kind of style. For example, this kind of style. And this is another style. Something like the Disney kind of baby. They have a very large shape changes. So the idea actually is not very similar to the original one. Yes, okay. Here are some more demo results. This is another, another style. Actually, based on this kind of algorithm, we can generate a lot of styles. Suppose we have the training data. And we can also use this kind of cartoon results. For example, if we do the tracking, we have the expression package. So we can use this cartoon result to do the to generate the expression package. And we also use the cartoon results in the game. This game actually is a very famous game in Chinese called 王者荣耀. Okay, now let's move to the next part. The next part actually is the face attribute editing. And there is one important thing I need to show is the ID and attribute. For example, it's very similar to the previous cartoon generation process. For example, for the cartoon generation process, we also need to maintain two stuff. The first one is the ID. We need to generate a photo, a cartoon photo, which is very similar to your input. For example, we need to maintain the ID. So the ID is very important. Another one is the style. We have the cartoon attribute, cartoon style. So we also need to the output similar to the cartoon style. So we need to maintain both. And for the facial attribute editing actually is very similar. For example, the import actually is for example, your image, and the attribute can be a lot of things. For example, I can change the age of your photo, change the expression of your photo, change the lightening of your photo. All these kind of stuff is we call it attribute. For example, the cartoon style is another kind of attribute. So the attribute is a very general word. And for this kind of facial attribute editing, we use the style GAN pipeline. There's two important components. The first one is the gain inversion, and the second one is the attribute disentangle. So let's move to the first one. What is the gain inversion? The import actually is the import of your face. For example, then what we want to do, for example, we will change the age of your face, right? So the first thing we need to do is to use the gain inversion to map the import user image to a latent code. Based on the latent code, actually, we can use the star gain to generate the original image. So the gain inversion actually is a kind of process the input is user image and output is the star gain latent code. And based on the latent code, we can generate another image, which is very similar, but actually there's some kind of difference to the original input. And based on the latent code, actually, we can do a lot of attribute editing. For example, we can attribute the age. Suppose we know the direction to editing. So the important thing, the core component for this kind of attribute editing is how to find the attribute direction to edit this kind of latent code. Actually, there are a lot of good work can do this kind of job. For example, like the interface scan, and there's also some kind of semi-supervised or weekly or self-supervised learning to find this kind of direction. And here we show you an example. For example, like we call it's a PSP encoder. This kind of algorithm actually import is a user image, and they map the user image into a style. And based on the style, actually, the style generator can generate an image with different, for example, we can do the game inversion based on this kind of process. And we can also do the attribute editing. For example, we can change the latent code here, and we can generate another image. For example, change the color of this kind of image. So this is an example we can use to do the face attribute editing. Actually, there are also a lot of good work which can do the same thing. And here we show some kind of results. The first one, actually, the input, for example, is this kind of image, right? And output, actually, they can make this guy to be bald. And we also have some results like this. We can change the ID of the result to more similar to the game ID. And here are two more demos. The first video actually shows you to change the attribute, to change the expression of this guy. The input, for example, is the first column. And the second column actually is to make the input user to smile. And the third column actually
Hello, hello. You can, Doctor, you can. I think we cannot hear you. I think maybe Dr. Yugan's internet.
sorry, there's some kind of network problem with my computer.
Okay, it's okay.
Okay, can you see the screen and hear my sound?
Okay, now I can.
Okay, okay. So let's just repeat this part. The input of this one actually is this kind of user input, user video, and the second column just to change this expression to make this guy to smile, and the third column is to make this guy to remove the expression. And in another video, this kind of example actually change the age. For example, this is the input, and this is to make this guy a little bit young, and we can see the difference is obvious. And we can also use this kind of algorithm to do the face reenactment. The job of the face reenactment actually is just like this. For example, we have a source image like this, and we have a driving image like this. So we want to use the ID from this source image and the expression from this kind of image. So we use this kind of image, the expression from the driving image to drive the source image. And here we can see the result. For example, the ID is just look like similar to this one, and the expression actually is very similar to this one. So face reenactment actually is also one kind of example to combine the ID and the attribute. The ID is just like this one, and the attribute actually is different expressions. And here we can use the, for example, like the first order motion model to do this kind of algorithm. And the idea is just like this. We first do the key point detector, for example, to detect the important key point among the images. And based on that, we can use the first order Taylor expression to approximate the motion. For example, finally, we can get the dense motion pattern and we warp the feature, the encoder feature, and finally get the result like this one. Here is the one demo result based on the face reenactment. The input actually here is one image. For example, I take the photo maybe 1 month ago. And the result is we first change the attribute. For example, change the age. We can looks much younger than this one, right? And we also do the face reenactment. For example, we close the eyes and make a little bit of smile. If you take a look at this one, closed eyes actually is another driving video to drive this expression. And okay, so I just list the 3 applications if we can use again for the face generation. Here, I will move to the next part for the model compression. As I just mentioned, in the industry, we need to run this kind of GAN algorithms in the mobile devices. So model compression actually is a very important part. The first thing we need to run a model on the mobile devices is we need to have a very fast mobile inference framework. For example, in our example, we use the TNN. Here, this is an open source inference framework. It actually is very fast for different kind of mobile devices. And besides of the inference framework, we also do some kind of model compression, like we compress the network so that we can run efficiently on the mobile devices. Here are some kind of experience we list here. For example, the network structure, the flops usually lies on, for example, 100 million and to 1G flops. If we use a little larger models, the runtime speed should be very low. And also, some kind of operations are very fully optimized on the mobile devices, but some may not be. So we should use the operators which are fully optimized, because sometimes if one fully optimized operator can run maybe one order faster than those which are not fully optimized. So this is a very important part. Also, the quantization, for example, actually is very important and is also very useful if you want to run it on the mobile devices. And in our example, we also use the NAS to search the models, which is, for example, better on the mobile devices. Besides of the model compression, the data actually is another very important part. If we want to, for example, use this kind of to do some kind of GAN application on the mobile devices. Normally, if we use the pixel to pixel, they rely on the peer data, but the peer data actually is very difficult to obtain. So here are some kind of ways we can avoid use the paired data. For example, we can use the cycle GAN, as I just mentioned. We just only need two data from the two domain, but they do not have some kind of correspondence to be the paired data. So it should be much easier compared with to collect the paired data. Another good thing is that we can use the style GAN to generate the data. For example, as I just show you in one slide, currently the generation quality actually is very good. So given a random noise, actually we can generate a lot of, for example, the face image, this kind of images, and we can also use the GAN inversion and the face attribute editing to change the attribute of the face. So normally, actually, we can generate a lot of images if we want, but actually the training of the style GAN relies on some data. So if we have already have a large set of data to train the StarGAN, then it is possible we can use the StarGAN to generate numerous data for the training of the other task. And besides of the StarGAN, we can also use the self-supervised learning to train the data. And in the industry, actually, manual labeling and manual collection is also very important steps to get the data. Okay, besides of the data, the robustness is another very important issue we need to address. For example, we need to optimize the algorithm to different cases, like to be robust to the different lightning, different poles, for example, different occlusions. So normally we will collect different data to do this kind of optimization. Also, we should make the style, the attribute to be consistent so that the training should be easier. Okay, so let's move to the next part, again for the human generation. I will use the human post-transfer as one example. This is an example for the human post-transfer. The input actually is the source image and a reference pose, and the output is a synthesized image with the appearance from this image and the pose from this image. So actually, this is very similar to the face reenactment. For example, in the face reenactment, the input is the ID, the face, and another input is, for example, the driving video with another expression, right? So this is, we can consider as the ID. This can be the attribute. So we can have the future result, like the final result is similar with the ID is similar with this one, and then at the pose, the attribute is similar to this one. And here we suggest to use the liquid warp GAN to generate to do the human post-transfer task because of the good performance. And if you need to know the details, you can check this paper. And here I will show you some kind of results. This video actually is used the algorithm in last year. So the input actually is the human face, human image, like rest pose or A pose. And this is the generated result based on the driving video with different poses. You can see the result. Actually, if you see the details, for example, the hand, for example, the face, the result may not be very good because the generation, the complexity of this kind of task is much harder than the human expression transfer. And here are some results generated in this year. Also, besides from the GAN for the face and GAN for the human, we can also use GAN for the font generation. The task actually is like this. We have an input, for example, we have a user handwriting like this one. For example, we have 10 Chinese words, and we want to learn the style, the handwriting style of this user. And we can use for example, any word to generate the final words. So actually it's very similar to the previous, as I just mentioned. For example, this is kind of ID, and the handwriting style is kind of attribute. We want to combine the ID and the attribute to generate the final result. So this is the two examples of the final generated result of the font generation. You can see the result is kind of very similar to this one, but also if we take a look at the details, there's some kind of difference. Okay, here's another part. The GAN, actually, we can also use it as a tool. We can do a lot of other things. Here, I will just show you very simple examples. The two papers discussed here can be considered use GAN as a tool. For example, based on the style GAN prior, we can use the self-supervised learning to train the 3D reconstruction of the human, the face pose. The pipeline is just like this. Given import image and init mean shape, the init 3D shape of the face image, we can use the mean shape of the 3D MM model. And we can do some kind of data augmentation. We can have different poses. We can change the poses, and we can also change the, for example, the lightning. We can generate the pseudo samples like this. And after that, we can use the gain inversion process to generate the projected samples, because the gain inversion involves some kind of prior of the face. For example, we can take a look at these kind of projected results. Actually have very good quality, and based on different view of this kind of face, we can do the 3D reconstruction, get the refined shape, and based on refined shape, we can put it here. We can do the enumeration again and again, finally until the convergency. This is one example. We can use the GAN technique to do the 3D reconstruction. Actually, we can have a very good result because of the GAN inversion. They include some kind of GAN prior, face prior here. Also, this is another interesting work. It's called dataset labeling. This paper is called dataset GAN. We take the car passing as an example. It's very expensive to manually label a large set of image to train the model. Here, based on star GAN, actually, we can, in the first stage, we can add a label branch to the original star GAN framework like this, the label branch. And we can manually label this kind of generated images. For example, you can generate 100 images, and we manually label the, for example, this kind of car passing results. And then we use the manual label result to train this kind of branch. And based on after the training, we can use the StyleGAN model to generate, for example, more image pairs. For example, one car like this and the label like this. So we have the paired training data. Then we can train the passing model, for example, to get a passing result. So this is a very interesting work. We can manually label some kind of StyleGAN result and generate the training data. With the training data, we can train another, for example, car passing model or face passing model, something like that. Finally, I will make a conclusion for this tutorial. First of all, I would like to say GAN has already been widely used in a lot of mobile applications, for example, face, human, font, but there are still a large opportunities in the future. The identity versus attribute is very important for example, the face, the human, the font generation, as I just mentioned again and again. And we need to disentangle these features as well as fusing them. Finally, I will list several challenges in the future if we want to further improve the GAN applications in a mobile environment. The generation quality should be further improved. For example, how to generate high resolution with more details. For example, as I just mentioned in the human post-transfer example, the generation result for the face, for the hand, actually is very poor. So how to improve this kind of results is a very interesting research topic. Also, right now, if we given a video, we do it frame by frame. So there is some kind of temporal consistency issue. So they can make, so this is a very interesting if we have some kind of temporal consistent algorithm to optimize this direction. Also, robustness is a very important issue. For example, how to make the algorithm invariant to different lightning, different pose, different occlusion is very useful. And besides, the fine-grained generation is also very important. If we can disentangle different attributes and generate specific feature attributes, will be very interesting. And also, multimodality fusion like audio, text, video should be well explored. with the promising application in industry. For example, right now we have some kind of BERT algorithm. We can use the text to describe the image that we want, and we can use the text to generate the final image. So actually, it's a very interesting application in industry. That's all for my presentation. Thank you.
Okay, thank you, Dr. Yu. Thank you for your interesting talk, and we have a good overview of how we can is applied in the industries. So now we have several minutes to let our attendees to put some questions. So anyone want to ask Dr. Yu questions? Okay. Okay. If nobody have the name, maybe I can pose a question. Okay. Dr. Yu. So I know the GAN for image generation in fact is very computational expensive. So if we want to generate some high resolution images or videos, then how can you make sure it can be run on a mobile device?
First, I'd like to say right now the computational power for the mobile device is actually very high. For example, in some cases, the GPU actually is faster than right now the PC. And so another thing is that for the video, actually we can do it frame by frame, and for each frame, right now, as I just mentioned in these slides, we can use fully optimize the inference framework to do the model inference, and also, for example, the model compression is very important. Normally, we compress the model to a very small scale, for example, like 100 million flops. This is actually much smaller than the model used in the papers. And also, quantization is a very useful technique to speed up the models. So I think here some kind of tricks is very important if we want to put the kind of model in the mobile devices.
Okay, I understand. Okay, thank you, Dr. Yu. Okay, if nobody have question, I think we will come to the last presentation by me, which is context-aware mobile visual analytics. With a minute, I will share my slide. Okay. Hello, Dr. Xu. Can you see my slide?
Yes.
Okay. Thank you. I think now the audience number in our room is smaller than at the beginning. I think some of the attendees may go to lunch. Okay. Never mind. I will continue to do the last presentation. So my topic is context-aware mobile visual analytics, and I'm Chen Tao from Fudan University. And so in this topic, I will mainly deploy them from 3 parts. First, I will give a background introduction. What is context-aware mobile visual analytics? Then I will give 4 methods which in our group recently developed for the context-aware vision study. Finally, is the conclusion and some future work. So first, as we all know, the deep learning has made the computer vision and other kind of tasks like speech and texture achieves a greater success in these years. As a conclusion, this success can be attributed to 3 factors. The first one is high power computational resource, like multiple GPU for model training, and also available large data like multi-class, multi-granularity, and multi-scenario data. And in fact, there is also the third factor, which is I call it a simple context. In most recent study, we often assume the train and texture data are sampled under similar context with little changes. This means the train and the texture image, they often have a similar background, similar scenarios, or similar things. But this is not correct in the mobile environment. I will explain in this slide. Okay, so for the mobile vision analytics, there are several challenges, which is unlike the previous traditional vision, computer vision based study. The first one is limited resource, like in the autonomous vehicle task, in the mobile augmented reality task, and in various applications. This computational power and memory device and other capacity are limited. So this is one challenge. And another challenge is the changing context and things, and showing in the right figure. And we can see if we capture an image in an environment, then such image may go through different weathers or different conditions at other time. In this case, a model trained for one environment may not work when the time changes. So this is one situation. Another situation is like the mobile device. When you take it and walk along the street, you will go through different context, and the mobile device will record different sensors data, like the temperature, like the GPS, like the user uploaded comments. So this constitutes different kinds of contextual information. So this information and these changes should be considered in our mobile-based applications. So this is also one significant difference between mobile captured image and video versus standard video or capture analysis. So now, based on this analysis, we come to our proposed method parts. So the first method, I call it context-aware object motion estimation. In fact, we studied this topic about 4 to 5 years ago. It is from an autonomous vehicle program. In this task, our focus is to detect an object from a moving camera, which is installed on a moving vehicle. Then we determine the object status, motion status, whether it is still or moving, and also its moving direction. For example, and showing in the 4 pictures in the left, we can see if you are a driver, then you will see a car is moving in front of you from left to right. And also you will see a car is parked stationary on the double yellow lines. And in the left one and the bottom right one, you will see two persons. One is moving across the street, which is dangerous, and another one is a man, a lady standing stationary in the road. So I think these complex situations should alert the drivers when he is driving a car. So to address this problem, I summarized it into three challenges. And the first one is we find existing object detection works. They mainly work on a single image and cannot provide the object motion information. And the second challenge is existing motion detection techniques cannot provide either category or number of objects within the moving regions. And finally, all the current motion detection works cannot detect the stationary objects which are treated as the background. Yeah, this is the typical challenge because the current motion detection works, they mainly assume the camera is fixed and then they use simple background difference or other kind of modern techniques to find the moving person. But this is not working in our environment because our camera is moving and the background is also moving. So we need to find a technique how to detect the moving vehicle from the moving background. Okay, this is the our idea. We use the left figure to simply illustrate our idea. And so in the figure, we find from the optical flow, we find those moving vehicle or moving objects. Its optical flow is significantly different from its surrounding environment. Even though the surrounding building or its road also has some flow information, but we found this surrounding environment flow information is different from the moving vehicle, which means the moving vehicle has its special or its unique flow direction, flow magnitude, which has different distribution from its surrounding environment. So this is an idea and also inspires us to develop such a method to do the motion detection. So the right is our context-aware motion descriptor process. First, we propose an object-level motion descriptor, which I call CMD, to represent the object motion behavior. The second is the CMD utilizes the surrounding context of the package object within a video frame spatially and two consecutive video frames are captured by a moving camera temporarily. So I divide it into 4 steps. The first step is we try to create a context-aware histogram of oriented optical flow. And so in the left figure, you can see the flow is generated from the centering object and its surrounding rectangle flow fields. Within each rectangle, each flow vector is binned according to its primary angle from the horizontal axis and weighted according to its magnitude. Yeah, for example, for a flow vector in this area, we bin it to a nearest direction according to the right equation. After divide each flow vector into its nearest direction, we then come to our step 2 to measure the flow field information inconsistency between the center object and its upper left and bottom right. We measure their inconsistency. A straightforward way is like this equation. This equation is to give value of 1 to generate a binary vector U, only if this value is the object value is larger than its surrounding flow values. So this is a very straightforward way. But using this method for a moving object or stationary objects, we will produce like O1, O0, or half 1, half 0 binary vectors. So this will cause a problem. Will cause some stationary objects may also produce O1 binary vectors due to their reduced direction deviations. So we propose a new method to measure the flow field inconsistency. We apply a neighborhood value to measure the inconsistency. The neighborhood is represented by a key of FIB. This key, as you see, is like this equation, which try to get the maximum of FIB across the B prime. And so this is showing in the right figure. We can see for the straightforward histogram comparison, if the center object, this B value is compared with its directly flow field value in the same direction, then it will give O1, 0. But if we extend its beams by extending to a certain neighborhood, then it will give a different comparison binary vectors. So this binary vector will be more accurate and be more reliable than the original one. So this is our method to generate the orientation-wide soft margin operator. So now the step 3 is to construct the context-aware motion descriptor, which we call DMD. The DMD descriptor is to utilize FOB to replace the original one. The original plus 1 is to generate the original flow vector distribution, to generate the original histogram. But now we use the normalized flow speed value to generate the histogram, which can more accurately denote the value, the flow speed, the flow magnetic value in this rectangle box. So the last step 4 is the concatenation histogram of all the binary vectors from a pyramid HOF. To generate this pyramid, we use different orientation vector lucid from 2 power 0 to 2 power 5. And then for each pyramid level, we generate a different histogram. And this histogram are finally concatenated into a long histogram vector to denote the motion behavior of an object. So this is the evaluation on our self-captured video data set. This is the results. We use this method to determine the image of the object motion status at different background, different skills, and different camera vehicle relative speed. Our results can achieve consistently around 90% accuracy for all the cases. So this is our first work. And then after that, we come to our second work, which is a context-aware domain adaptive object detection. And just see in the mobile videos or the mobile scenes, the captured background keeps changing from time to time. So we need to design a method to try to uniquely identify those objects from dynamically changing background, like this picture shows. So to solve this problem, we first review existing method for existing unsupervised domain adaptation method for OD. We mainly use a labeled source image and unlabeled target image to predict the objects with domain states, but they have several limitations. First one is all these works focus on improving the domain adaptability of a region-based detector like the FastRTE family. And also, based on this FastRTE family, these methods try to align the instance-level features between domains by means of an RPE module. And the third one, this for the region-free detector, for example, the FFG and the YOLO family and the YOLO, which have no RPE module, these works cannot align the instance level features. The instance means an object or a rectangle box. The fourth one is performing the cross-domain adaptation without considering features from different thematic levels and spheres in all these existing works. So the existing region-based domain adaptation works have these challenges, and we need to address them in our work. So this is a typical adversarial learning process for domain adaptation, which is published in IDML 2016. This framework is very typical, and it is borrowed by many later works in this domain. So let's see how it works. In fact, as shown in this picture, the most important part is the red color dotted box, which is a domain classifier. It's how it works. First, for an input image, it first goes through the green color backbone feature extraction process. Then the extracted feature will go through a classification process. A classification process. This classification network will give a class label for the predicted feature, and meanwhile, in the domain adaptation process, the feature will also go through a domain classifier. The domain classifier will determine a domain label to determine whether this feature is from a source domain or from a target domain. If the domain classifier cannot discriminate whether the feature is from a source domain or target domain, this shows this feature extraction network is very good because it can extract a consistently representative features from both source domain and target domain. So this is an idea. However, such a domain discriminative network cannot include the domain invariant information from multi-level semantics. What it means, multi-level semantics, and we see this domain classifier only works on a single level feature F, on a single layer feature F. This cannot include multi-level semantic information. So this is a bottleneck of such method. So we propose following method to address this problem. And this framework, its idea is based on a single source object detection network like the FFG or refined data. First, for a labeled source image and unlabeled target image with quite different context or background, both of them are first fed to a feature extraction network. Then, in this part, in this position, it will first go through different levels of feature map extraction, and also for each level of feature map, it will go through our designed multiple DFEM modules to do the domain classification or domain adversarial learning process. Meanwhile, we will also go to the final prediction module to do the classification and localization for the detection task. So this red color dotted box is our contribution part. Next, I will give details for each module. First is the DFEM module. The DFEM module is full name is a densely semantic enhancement module. It is mainly used to try to extract the densely semantics from the original feature map F key. The F key is this one is each level of feature map. So the F key will first go through backbone. This backbone is to extract the signature features or the tasting features from the original feature map, and then it will go through adversarial segmentation process, and meanwhile the segmentation loss. This green color feature map will extract or will assign different weights to different locations. Then it is multiplied with the original feature map to generate an enhanced feature map. This feature map will give more emphasis to the foreground while weakening the background parts. Yeah. This is the first module. I call it a foreground enhancement. Then it will go to the multi-level semantic representations. This module, and we see, is like a definite structure. It tries to extract the different levels of semantics from this input feature map. This convolution block, H31 or H32, is a 3x3 kernel size with different deletion rates. Different deletion rates can extract different levels of semantics information from the inputs, and then all the outputs from each level of dilated outputs will be concatenated together to form a final feature map, and then goes to a one-by-one convolution to reduce its channel number. And this way, and this original output feature map will further go to a multi-scale feature encoder block. This multi-scale feature encoder block, and showing in this figure, will pour the original feature map, this feature map, into different size of feature maps, 1x1, 2x2, 4x4, and 8x8, like a pyramid style. These different spatial resolution features will be upsampled into a uniform size to concatenate together, and finally go to the final discriminator part, and go through the and use to compute the adversarial loss. So this is the DFEM module. So this is the overview of the foreground enhancement module in the DFEM part, and we see the input foreground feature map will go through around 3 blocks of dilated convolution units, followed by a ReLU activation function, and to get the segmentation mask or the attention mask. And this mask is used as a weighting factor to be applied on the original feature map. Yes, this is the foreground enhancement module. And for the loss function, we use three loss functions to do this task. The first one is the source domain detection loss, and this one is a common loss in most domain adaptation works. And the second one, we call it adaptive foreground augmentation loss. This one is used to focus on this foreground discriminative adversarial learning process. And finally is the adversarial loss for the whole image or whole feature map. Yeah, which is to align the features of the source and target domain in the whole level, in the global level. So this is the result of our method. We can see in the BlitzNAV study of TIBOR1, we can see with the foreground enhancement module, the performance is consistently improved with each level of L. And also we increase the number of L, which is the semantic levels. We find the levels when the level L equals to 3, the performance is the best. And in the second study, we study the impact of multi-scale feature encoder functionality, and we found the method of proposed FFT with our multi-scale physical path P, which is 1, 2, 4, 8, achieves the best performance. Yeah, this also shows our proposed multi-scale physical path. And we also do experiment from natural images to enemy images, and we find the proposed FFT always achieve the better performance than other method. Okay, we also give some pictorial results of our method. The first column is the original image captured and different background. The second column is the local alignment. Yeah, we can see the local alignment can only capture the detailed features in each picture. And also we show the global alignment ignores multiple instances like this one. Like the first picture, we can see it ignores several birds in the image. And with the DSEM, which is the densely semantic enhancement module, it can capture both the instance and also the detailed features of the whole image. And this is the result in other datasets, cartoon and ink painting dataset. And this is the results without DSEM and one is without DSEM, second one is with DSEM adaptation. We can see after applying the DSEM adaptation, more vehicles and more small-scale persons are identified using our method. So this is the second work. So now I will introduce our third part, our third work, which is context-aware dynamic predictory intrusion detection. So what is a context-aware dynamic PID task? In fact, it is in comparison with the static PID, which is trying to detect the abnormal persons from the static scenes captured by a fixed camera. As shown in the four references, we can see this work is trying to detect the vehicle or the person from fixed camera scenarios. Yes, and this works using different kinds of methods, like the Retinex enhancement method, like the GMM and SVM method. Yes, all these methods are traditional machine learning methods. So different from the static PID, our work is trying to detect the predictive intrusion case from a dynamic videos, which means the object or the scenes keeps changing and recorded by a moving camera in a vehicle. So to solve this case, our proposed method is based on a PID net, which is designed by us. We use a developed PID net to detect the intruding predictions from moving videos. So this PID net is mainly based on two stages. One is AOI segmentation, the area of interest segmentation, and the second one is the prediction detection in the AOI area. So this is an overview of our proposed PID network. This PID network is mainly consisted of two key parts and shown in the red color dotted box. First, for an input image, it first goes through a state backbone to do the feature extraction. Then in the upper part is a segmentation branch, and the lower part is the detection branch. And finally is the result of the segmentation and the detection fusion to give a final decision on whether the prediction is an intruding person. In this case, we pick a person working in a road as an intruding person. So in the segmentation branch, we use we borrow a similar structure from ByteNet, to do the root area segmentation. And you see in this root area, after the root area is segmented from the original image, we then crop the root bounding box, and using this bounding box and throwing in the green color part to do further RPE module prediction detection. Yes, this detected predictions within these ROI modules and is fused with the original segmented root area, and we are masked to get whether the detected prediction is standing on the root. So this is the roughly idea of our PID network. So in this process, in order to speed up its inference time and also save the memory requirements, we make some modifications to the backbones. In the original backbone of ByteNet, the left part is 64, 128, and 258 G-by-G convolutions, and we change this convolution into depth-wise convolution, but increase its number of filters. This number of filter increase will not change its total size and will not bring the inference time increase. On the other hand, it can decrease the inference time. So this is our speed sharing design. So this module is applied on this feature extraction part. So the second one is the feature grouping design. To speed up the prediction detection process, we don't want to do detection on the whole image. Instead, we want to only detect the person in the sub area of the image. This sub area is derived from the segmented AUI, segmented root area. So in this root area, the minimum rectangle box around this root area, we do it and crop this box to do the detection of the human. So this is the feature cropping design. And finally is the feature compression design. We modify the fast RDA module to our new approach. And this part, G-by-G convolution, is replaced by 5x5 depth-wise convolution. And also we replace the original 3 fully connected layer into only one, and also reduce the number of neurons to half of its original size. So in this, by this method, we can greatly compress the original network size and the inference speed. So this is the data set, and there is no intrusive data sets and dynamic changing scenes. So we create one from a combination of CityScape and CityPorcine. In the CityScape, the dataset it gives a segmentation pixel label for all the pixels in an image. And for CityPorcine, the portions are given a rectangle box. Then we start to locate those portions and standing on the root area and label them as Y. Y means this portion is treated as an intrusive case on the root area. So after dataset creation, we then create such a dataset which is totally more than 15,000 non-intrusive and more than 4,000 intrusive cases. And also we do the intrusive detection experiments on the datasets and find our results gives a high value of 49.2% PID MAP, and also with 5.4 FPI inference speed and 138.7 parameters, which speed is faster than the original segmentation backbone and the detection backbone. Also, this is the illustrative examples for our PID cases. We can see those persons standing on the road are always correctly identified using our PID detection network. And also, we do a listening study to study the FT module, the spatial path, and the context path, and our 5x5 depth-1 convolution, and other modules. We can see the results consistently improved with the aid of our design modules. And so this is our third work. So now we want to introduce our final work, which I call it context-aware rapid semantic segmentation. The semantic segmentation is a very familiar topic in this computer vision study, which try to predict a pixel label for the whole image. So I will not spend too much time on this part. And there is an increasing desire to design the lighter weight semantic segmentation neural networks due to the autonomous vehicle or other FPGA or resource-constrained devices, as I just mentioned before. And in this part, we need to consider several factors to design lighter weight neural network. The first one is inference speed. Yeah. And the second one is the number of parameters of your model. The third one is the flops. And the final one is the accuracy. So your focus is try to get as high accuracy as possible and limited flops, number of parameters, and with high inference speed. So this is a summarization of existing lighter weight neural networks, and we can see those networks are mainly located in this area, in this figure, where the horizontal axis is the number of parameters, and the vertical axis is the accuracy. We can see the red color with EEDNet, which is designed by us, achieves the optimum trade-off between number of parameters and accuracy. So our EEDNet work is a principle, is a working idea, is mainly based on the following. First, we see the first problem is there are lots of irregular rectangle objects, like in this picture. Yeah, this van and this pedestrian and this pool, they have quite different aspect ratios and shapes. So this irregular rectangle object with different scales in these urban images cause the traditional square receptive field network with a common 3x3 convolution units cannot effectively match with these objects like this. A traditional 3x3 kernel filter will produce a mismatch with these different aspect ratios of objects. And the second problem is currently there is a lack of convolutional block which can extract the contextual multi-step with less parameters and low computational costs. Yeah. So this is the two problems we are facing to address this problem, such a task. So in view of this, we propose a method which is inspired by two ideas. The first one is we find a 1x3 and a 3x1 asymmetric convolution group can replace a traditional 3x3 convolution. In fact, these findings is always found and proved to be right in most studies. And the second one is inspired by the fast-acting anchor box design scheme. Yeah, using different skills and different aspect ratios anchor boxes to detect the different objects. And our contribution is to combine such two kind of scheme and apply a different deletion rates on the 1x3 or 3x1 arithmetic convolution unit, and then they will form such kind of multi-scale and multi-step receptive field convolution unit. This, for example, this yellow, this red, and this purple color box will be able to localize the objects with different aspect ratio and different scales, different shapes. So this is the convolution. This is the roughly idea of our designed convolution unit. We can see in this designed convolution blocks, it has 4 branches. The first branch is a 1x1 convolution to do the channel reduction, and then go through a 3x1 and 1x3 convolution with the dilation rate of 1. The second branch, third and fourth, will also go to a 1x1 convolution to reduce the channel number, and followed by 3x1 and 1x3 depth-wise convolution with different deletion rates. This different deletion rate group will form such kind of different receptive fields of convolution units to capture the information of the object. So this is the this is the first module of this block. We call it this is also inspired by the bottleneck and the high pass width structure, and also depth-wise convolution and derivative convolution is used in each branch. And then we go to the transform fusion part. This part is applied after the branch merge part. We can see we use a 3x3 depth-wise convolution and a concat and a 1x1 convolution to restore the channel number, and then the restored channel number will be added with the original inputs like a pass width structure to form the final output. So each branch will capture the deep multi-scale and multi-step receptive field, and the transform fusion part does the feature matching and the restoring function. So this is the our designed convolutional block to capture the objects with different shapes and scales. So based on this designed block, we call it a multi-receptive field and a multi-step MMFD block. We then insert different numbers of MMFD block N1 and N2 after the after several downsampling convolution blocks to form a very compact and very fast rapid semantic segmentation networks. And we can see in this backbone, we call it EEDNet, efficient arithmetic network, consists of 3 downsampling blocks. One is the concat block by 2 parallel branches. One is a differential depth-wise convolution block, and finally is the depth-wise convolution block. These 3 specially designed downsampling blocks works in different layers in the whole network structure. And also, skip connections are used to combine the detailed information and the semantic information. Like this one is from the cellular information, and this one is from the high-level information. They are combined and then go to a 1x1 convolution to give the final semantic prediction levels for the input image. So this is our EEGNet structure. And we also experimented with different numbers of A1 and N2 to give the optimal number. So EEGNet is found to be the smallest semantic segmentation network amongst state-of-the-art lightweight networks. And the EEGNet also achieves a competitive performance in CAMVID and CityScape datasets. EEGNet also has a faster inference speed, less flops, and a strong feature extraction ability. We can see compared with FlagNet, EFNet, ENet, DFANet A, and EFPNet V2, our method achieves a very fast inference speed with only 23.98 milliseconds and such resolution, and also its FPS, flops, parameters, and MIOU are most competitive among all these methods. And also, this is a comparison, visualized comparison of different methods for the cityscape dataset. We can see our method and with this input size resolution achieves 5.99 flops and 68.3 MIOU accuracy. So this is our fourth part of context-aware semantic segmentation part. And finally, I will give a conclusion and future work. So for mobile-based visual analytics, in fact, all the research are trying to focus to address two challenges. One is limited computation resource. Another one is limited data with changing context. For the first challenge, we need to consider the memory consumption, the inference speed, and also the bandwidth. Bandwidth is usually ignored by the researchers. In fact, bandwidth is very important. And you know, memory consumption and inference speed is very important in this to speed up the inference time. But bandwidth, which means how much bandwidth it will consume to move the data or to move the parameters from the RAM to the processor or from the case to the processor. If it consumes a lot of bandwidth, then your model efficiency will be quite low. So we need to design a model with less parameters, with less flops, and also you need to be your model structure will also consider how to communicate between the processor and the cache or memory. So the communication scheme between the data is also another consideration in mobile-based AI model design. So for the second challenge, limited data with changing context, we need to consider different contextual information. The first contextual information is in the image. For example, we need to consider the target objects, its surrounding pixels or surrounding objects around the target objects. This surrounding context is useful and important to give a prediction for the target object. The second one is the context in the device. For example, for the mobile device with various kinds of sensors, it will record, for example, the GPS, the compass, the direction, and also the axis parameter, or even temperature. This contextual information in the device should also be considered to deploy the AI model on the mobile devices in the future. And finally is considering the limited data captured by the mobile device. We need to incorporate the few sorts of weakly supervised learning into this kind of contextual learning process. So I think that these factors should be considered in the mobile-based AI study in the future. So this is published works for context-aware analysis in our study this year, and this is my presentation. Thank you. That's all. Okay, so I found that there is only one attendee in this Zoom session. So do you have any question? Okay, I think if there is no question, I think our tutorial on mobile visual analytics will be end here. Okay, thank you. Hello, Dr. Yu, are you there?
Thank you. Thank you. Bye.
Okay, thank you. I think it's already very late. We can end up here.